Welcome back. As we look at evaluating triple integrals within cylindrical coordinates, we realize that the procedure is very, very similar to how when we previously defined triple integrals in rectangular coordinates. So our first function z, we see we're passing through a upper and a lower surface. We're entering a surface, so that would be my lower bound, z a function g sub 1 of two variables, and then exiting, z is g sub 2. Both of those are functions of two variables, r and theta. So we've got dz. Notice we have this extra integrating factor here, r. Just like with polar coordinates, we're also going to have that extra r value that we have to put in with cylindrical coordinates. So then we look at integrating with respect to r second. So r is this radius. We have a inner radius that we touch first, and then we go out. We have an outer radius. So the radius, or the radii functions, those are functions of single variables, r being a function of theta. So we have a lower bound and an upper bound, inner and outer. And then, of course, theta, my third variable that I'm integrating with respect to here, that's just a rotation from some initial alpha. So initially we rotated over here to alpha, and then we have a terminal side of the rotation, that is my beta. So we've got our alpha and beta. So take a second, look over that, make sure it makes sense. It's really the same thing as when we previously defined triple integrals in rectangular coordinates. And then just when we're dealing with polar, we always have that extra r factor when we integrate. So let's hop right in and do an example. Here we're going to evaluate the integral given in cylindrical coordinates. Notice we have no integrand, and we also have this extra integrating factor r. So integrating nothing with respect to z, we're looking at just this piece of the integral. That's going to give me z. So my bounds on theta are still the same. My bounds on r are the same. I integrated nothing, and I got z. So these two functions were z in terms of r and theta, and they're really rather simple. It's actually just z in terms of r. So plug this in. I will get 3 plus 24r squared minus 0 is going to give us just the 3 plus 24r squared, which leaves us with a product, bringing that r in as our integrand. So working through this, I'll have 0 to 2 pi, 0 to theta over 2 pi, and that gives me 3r plus 24r cubed, dr d theta. So now we will look at integrating this inner integral using the power rule, which leaves us with 3/2 r squared and 24 over 4, which is 6, r to the 4th. And we're going to evaluate, these bounds are in terms of r. So r is theta divided by 2 pi, and r equals 0. So plugging that in, I have 3/2 theta over 2 pi, quantity squared, plus 24 over 4 is 6, theta over 2 pi, quantity to the 4th, and then plugging in 0, we'll just get 0, so we don't need to write that as a subtraction. So now we need to simplify this integrand here, which I now have 0 to 2 pi. So what do we have inside? I have theta squared, so 3 theta squared, 2 pi squared is 4 pi squared times 2, so I have 8 pi squared, plus 6 theta to the 4th. 2 to the 4th is 16, so that's 16 pi to the 4th. And 6 over 16, I can pull a 2 out of each of those. So that gives me 3/8. So I have 3/8 again. And we will integrate that with respect to theta. So as we look at integrating, keep in mind that 3/8 and pi squared, that's a constant. So we're just going to use the power rule on theta squared and theta to the fourth. Same over here, 3/8 pi to the fourth in that denominator is a constant. So let's look at what we have. I have 3/8 pi squared. Dealing with just this theta squared, that will be theta cubed over 3 plus, I have 3/8 pi to the fourth, and integrating theta to the fourth, that is 1/5, or we'll just say theta to the fifth, over 5. And now we need to plug in theta equals 2 pi, and theta equals 0, and we will be almost done. So before I plug in, I do notice these 3's cancel, which is kind of nice. Nothing cancels in the other fraction. So I have 2 pi cubed over 8 pi squared plus 3 times 2 pi to the fifth over 40 pi to the fourth. And now I have 8 pi cubed over 8 pi squared plus 3 times 32 pi to the fifth over 40 pi to the fourth. The 8 and 2 of the pi's cancel, so this first term just turns into pi. And 3 times 32 divided by 40, that's going to give us 12/5. And I'll have 1 pi in the numerator, so plus 12/5 pi. And we end up with 17 pi over 5. That is the answer when we evaluate this triple integral in cylindrical coordinates. All right, good luck out there. Email me with questions. Be safe. Have fun. Make good decisions.